G'day viewers. In this segment I'll talk about the performance of the HTTP protocol. So we've covered an introduction to the HTTP protocol and heard about its requests and responses, but I haven't said anything yet about how well it performs over the web. That's what we'll begin to look at in this segment, and in particular I'll go over a couple of options for arranging requests and responses, so-called parallel and persistent connections. Now, for any discussion of HTTP performance for loading web pages, we need to understand what we really mean by performance. What is it we're trying to improve? For the web, the most direct thing that we would like to improve is page load time, or PLT. This is the time from when a user clicks on a link to summon a page until something useful appears in your browser. So it's a very user-centric measure. It's what people usually care about when they're designing websites. Note that it's actually different from situations such as when all of the content has been transferred in your browser, for instance. That's not really what matters. Or even the lifetime of the HTTP connection. Again, that's not really what matters. For the user, it's really the moment from when you click until you see something useful on the screen. And there are subtle differences between all of these different definitions. Unfortunately, for us, in terms of understanding it, page load time depends on many factors. It depends on how you structure your page. You may choose to have many embedded objects, different pictures that are part of the page, which are fetched by separate HTTP requests, or not. This would affect how quickly the page can be loaded. The page load time depends on the details of the HTTP protocol itself, as well as the TCP protocol. We'll see that TCP factors like time to set up connections and slow start behavior actually matters, depending on how HTTP mixes and matches between requests and TCP connections. And of course, the page load time depends upon the network itself. And it will turn out that it depends not simply on the bandwidth of the network, but it also depends on factors such as the round trip time. What I forgot to mention here, just that page load time is not just a hypothetical metric which is useful in theory. It's known to be useful in practice in that there's been much quantitative work, especially around online e-commerce. And sites find that small increases in page load time can actually decrease sales measurably. Amazon has a lot of data on this, for instance. So they very much care about keeping a good page load time to keep all of their customers happy. Okay, so now we want to understand how page load time works, or at least what kind of page load time you could expect for different versions of HTTP. So let's begin at the beginning with the earliest versions of HTTP. And the simplest thing you can do is to send one HTTP request and receive a response for it on one single TCP connection. If you have other requests to make, use other TCP connections for them. This is how that would work. So imagine that I'm trying to request a page, fetch a page, and it has the main body of the page and maybe a couple of inlined images. Well, first of all, I would set up a connection for the page. This is the connect. Then I would send the request. Then I would get back the response. At that stage, I might have the body of the page. I'd look at it, I'd see that there are inlined images. Well, I would then set up another TCP connection for the inlined image. This is the request and this is the response. And then I'd send a request again, get back a response. Actually, maybe it's a fairly big response because it's an image, but I would be done with it eventually. Then I'll set up the third connection, send the request, get back the response, and you can see where I'm going. So this is one TCP connection, two TCP connections, three TCP connections. This design was actually very easy to build to begin with because TCP is essentially giving you everything you need. On the other hand, it gives a fairly poor user experience in terms of page load time, as you might imagine. So let's dive into that. First of all, let me clean up the diagram so you can more clearly see the connection setup. It's just some delay for that. And the request and response. Now, so why does this give poor page load time? Well, there are several reasons. If you think about all of this behavior here, you can see that this is inherently sequential in the way we've structured it. So none of these steps are going on in parallel, we just have to wait for them all to happen one after the other. This is the case even when we're talking to different servers. Now you'd think one of the reasons you'd have a network is that you could talk to multiple servers at once and overlap activity between them. You can, we're just not doing that here. And because we're sending only one request per TCP connection, this means that we have all of the overheads of a TCP connection for every request. So in particular, we have like 3 connection setups, when if these resources all came from the single server, we would only really need 1 TCP connection set up to it. More than that, we're also suffering from TCP slow start at the beginning of each of these responses when a larger volume of data tends to be returned. TCP needs to start slowly and then ramp up and rediscover the speed of the network. We don't have a single connection that's up and running and we keep sending the data down it. Instead, we're doing 3 things independently. So for all of these reasons, we're not making very good use of the network. You might want to just stop the video in just a moment and think for yourself about how you would go about improving this. Improvements are certainly possible, that's exactly what we're going to see, but it takes a little bit of thinking to understand how you might come up with the improvements. So why don't you see if you can come up with some of the options that we'll get to. And I'll mention just the broad approaches on the next slide. You should be able to see, just to start thinking about what's wrong with this, that in this picture the network is not used effectively because only some blocks here are shaded in grey when I'm actually using the network at any significant rate to send back the information. The white time the network is mostly idle. Actually, even in that grey period, slow start is going on, so we're not using the network very well. So there's a lot of inefficiency there to be gained. This picture gets worse, if you think about it, when you have many embedded resources that are part of a page, because we'll then have many more connection setups than we would otherwise have. And it's also worse, not only if you have many resources per page, but if you have small resources per page. Because for these small resources, we're not really ramping up, a big data transfer in these shaded periods to amortize all of the costs of connection setup and slow start. If each of these individual grey areas was a very large object, well, maybe it wouldn't matter if we had a few overheads to go with it. But if they're small files, then these overheads can really add up. So here's that slide that just outlines some of the categories of approaches we might go about for improving page load time. And we're going to get to most of these in more detail over the coming lectures. The first approach is simply to reduce the amount of content that we need to transfer. You could imagine doing this in a few ways, and this is something that's still very much popular today. It used to be that you would try and reduce the size of the images that you'd have on websites just to avoid unnecessarily large images, for instance. That's something you can do. If you wanted to, you could use better compression formats that are suited to the kind of image you have, so they're going to make it smaller. You could gzip some of the contents. As far as smaller images goes, for instance, note that a server might want to send a different version of an image depending on the client. If you have a big browser running on a computer that has a big screen, you might actually want a fairly detailed picture. On the other hand, if you're operating on your smartphone, there's really no point sending a high-resolution picture. So the browser would actually like to know from the client which situation it's in these days. That helps you send the appropriate content. So that's one approach, send less content. And there are opportunities for that. Another approach is to change the HTTP protocol to make better use of the network bandwidth. This is what we're going to get to in this segment, and I'll tell you more in a moment about how we might do that. And then there are other big approaches that we'll get to later. So another big category of approach would be to leverage repeated visits. For many web pages, it's the case that for a popular web page, you don't visit it just once, you visit it many times. If maybe you visited it every single day. If every time you visit it, all of the contents of the page is sent across the network, we're transferring the same information many times. What we could try and do is change the HTTP protocol to avoid these repeated transfers. This is called caching. And we'll look at caches and other devices which perform caching, such as web proxies, in a subsequent segment. And then finally, here's another category that you might not have thought of, and you can use this for popular content. You can move the content from the server, which might be remote, to locations that are closer to the client. This is going to have the effect of reducing the download time. This is the strategy that content delivery networks use, and we'll get to see that later on. Okay, but for now, let's dive in here and look at how to change HTTP to do something different than that single request per TCP connection sequential style we just saw to get better performance. What can we do? Well, here's the first thing you might think of doing, and that is to run parallel TCP connections. Why run one TCP connection one after the other, when in fact there's no reason you can't write a program to open many TCP connections at once? So here's what we would do. You would have your browser run, say, 8 instances, some small number, more than one, of the HTTP protocol in parallel. Each of these instances would have its own TCP connection and would send one HTTP request over that one TCP connection. These TCP connections are just happening in parallel rather than sequentially. You need to change your browser to do this. Interestingly, you probably wouldn't need to change your server. Servers are already used to being able to handle multiple concurrent connections. Usually these are connections from different clients. That's why they were built to support that, since you don't want to sort of block one client while you're serving another client. You'd like to be able to serve many of them in parallel. If that's the case, then the server can already serve multiple requests from the same client in parallel. It just drops out. Now, what you might wonder is, how does this strategy of running HTTP connections in parallel help us? I mean, after all, if this could simply be a different way of slicing up the pie. Instead of giving each user 100% of the network for 1/n of the time, you could give n users 1/n of the network for all of the time. It would all add up to the same thing. I hope I got the numbers quite right there, but I think you know what I mean. Giving someone all of the network for a small portion of the time versus always using the network but only getting a fraction of its capacity. If this was the case, it really wouldn't matter if we performed our requests sequentially or parallel. They would take the same amount of total time. But this is not the case, because the key observation here is that the single HTTP connection wasn't actually really using all of the network that much. It wasn't using all of the bandwidth. That's why we had a lot of white on the figure before. During the connection phase, we're really just waiting around for the two ends to synchronize themselves. We're not limited by the network bandwidth. That means if we run our connections in parallel, they're not going to be slowed down by very much, because now they're actually making use of something that they weren't using before. If that's the case, we'll pull in the last one to complete, and that will reduce the page load time, so we'll be better off. So parallel connections are something which is widely used in practice. But there's something even better that we can do, and this is called a persistent connection. Now, parallel connections help, but they're not a panacea, they're not ideal in a couple of respects. Actually, the important respect here is that something that's a little odd about these parallel connections is that even though they're all coming from one client, they're competing with one another for the network resources. So by writing a parallel client that maybe ran 8 connections at once, that one parallel client might appear to the network as though it has the same load as 8 sequential clients, because that's the behavior that it's providing. If that's the case, we're sort of multiplying the number of clients which are trying to use the network at the same time significantly, as far as the network's concerned. And the effect is to exacerbate the network usage. Usage tends to be more bursty, and this leads to larger amounts of loss, which then have to be recovered by all of the protocols. In fact, if you think about this, while we're downloading 8 connections in parallel, one of your connections might cause loss for another 3 of your connections, which will then have to realize it and deal with it. So the network doesn't operate very smoothly here. The alternative which we can use, which gains us many of the performance advantages of parallelism, yet is more effective in terms of network usage, the usage is more well suited to the network, is what is called a persistent connection. Here, what we do is we simply make one TCP connection to the server. We don't make 8, we just make 1. And then we use this one connection to send multiple HTTP requests. So let's see how that would work on some of our time sequence diagrams. Here we are. So let me just draw in just for reference, here's how it used to work when we had our first scheme with the connections and then request response. So connect, request, response. And I'm just doing that repeatedly. Let me just do 3 of those. And actually I'm also just going to indicate a bigger volume coming back on these responses. Okay, so for persistent connections, here's how it would work. You would, first of all, you've got to make your TCP connection. You can't get around that. Now you send the request. Now you get back the response. Okay. Looks just as usual. However, now we've got back the page and we found there are a couple of embedded inline images. What do we do? With a persistent connection, we don't close this TCP connection and open another one. We send the second request on the same TCP connection and we get back the response. Then we send the third request and we get back the response. Now this is better in several respects. You can see we only have one TCP connection. It's a little hard. I'll clean this up in a little while. Actually, why don't I just go through the options and then we'll talk about why it's better. You'll notice that there's on this persistent connection I only had one TCP connection and then I sequentially sent the request response pairs. There's something even a little better we can do, and that is this option. I'm going to make a connection. Do the initial request and get the initial response back. You can't do much before that. Now at this stage we've got back the body of a page and it has 2 inlined images, say. What we can do now is send both requests right away. Why wait? Just tell the server what you want right now. As the server gets these requests, it can start answering them. It'll answer the first request first maybe, then it'll answer the second request. So really the answers for these 2 requests have been combined together. We're not waiting this extra round trip time sort of here to be able to send the request there and get the response back. So let me just clean that up. Here it is. And now I'll discuss it a little bit. So you can see in moving from the 1 request per connection to the sequential requests over here, we benefited from having only a single TCP connection. Yes, that's good. So we would expect sequential requests to be better. We're actually doing better than that though, because you'll notice for some reason I shaded this grey area to be much shorter in time than it was on the first one. What's going on there? Well, what's going on here is that, let me just write no slow start. What's happening here is that we already have a connection up and running and we don't need to perform slow start for it once again to be able to send more content. So we're beginning to use the network quickly to all of its capacity. So we should be substantially better off under this model than the previous one. And you can see that we can be even better still as we move to this model. Here the difference is that those 2 requests here have been gone out at the same time. And so now the information comes back to back. We don't have the gap. Right? So I'll tick that. This gap over here has gone. And we're somewhat better off. So by performing all of these steps, we're beginning to use the network much more effectively than we would otherwise. And parallel persistent connections are what is used in modern web browsers today. Just to finish, I want to discuss HTTP 1.1 with persistent connections a little more. Actually, so it says these persistent connections were one of the major changes which were introduced going from HTTP 1.0 to HTTP 1.1. Pipelining is an optional mechanism in this standard. Initially, they were just persistent connections and pipelining wasn't implemented. Over time, pipelining has come to be implemented more widely. And so now we have persistent pipeline connections in browsers. This helps the page load time for all of the reasons that we just went over in the previous slide. Now, I would actually like to be able to give you some figures and just say, well, how much benefit you get from all of these different techniques. That's very hard to do in the abstract though, because the page load time benefits you get are going to depend on the structure of the pages, including how long all of these contents are, as well as the network itself. Nonetheless, we would expect to get many of the benefits of speeding up the network transfer, maybe not all of parallelism actually, but we come up with a workload which is much easier on the network in terms of causing loss and so forth. Persistent connections aren't all roses, however. They do raise a couple of issues for us to think about. One issue that you have to think about if you implement it is how long you keep a TCP connection open. It's fairly easy for me in my example to say, well, I have this TCP connection, I keep it open, I send the 2 requests, which I happen to know were there, and well, then I could close it. But in reality, a browser and a server wouldn't know whether to expect any more HTTP requests to the same server or not. It just depends on the contents of the page that they don't know yet. More, and whether the user interacts with the site. More might be coming or it might not. So typically browsers and servers will hold persistent connections open for a very short amount of time, and if there's no continued activity, close them. Particularly if a server is busy, it won't want to keep extra connections around. And you might also wonder whether it's possible for persistent connections to be slower than parallel connections. Well, the answer is yes, they can sometimes be slower. Why is the question? Well, to think about this, consider what will happen if you have a web page which has many small components in. In that case, the network will be mostly in slow start because it won't really have the time to get up to full speed. With persistent connections, we're going through a slow start once. With parallel connections, we're also going through the slow start, but all of the connections are slow starting in parallel. So if you like, it's a faster slow start. Because of this, actually the TCP connection details often matter for web page load performance. And one thing you might do is configure your TCP to use a larger initial window size. This is a common practice on the web today. Okay, so that's all I have to say about persistent connections, and you now know how requests and responses are sent over TCP connections.